Are there any questions over the homework assignments from yesterday or Tuesday? Factoring worksheet 1 or factoring worksheet 2? If there's no questions on those, we'll go on and start looking at the one from today. Now, the note sheet we're looking at today really isn't overly different. It's just these are special cases. These are special type of factors that work out in a unique kind of way. Now, the first ones that we look at is this one here, 4x squared minus 4x plus 1. Now, we're going to go on and factor this the way we normally do it. There is a special way to do it, but it's not really any faster or really any simpler than just factoring it our normal way. Now, since there's not a greatest common factor, we're going to go with our 2 sets of parentheses with 3 spaces. And the next step is going to be to find the sign. Since the third term is positive, our signs are the same and they match the sign of the middle term, which is negative. So we have negative and negative. Now we need to find the factors of the first and third terms. Normally, especially the last 2 days, we looked at the factors of the first term first, but we really don't have to stick with that. We could do the third term first also. And the reason I say that is, well, what are the factors of 1? 1 and 1. If it's easier to do the third term first, that's fine, because it's only one set of factors. They're both 1. We can throw them in. The same thing's true with our x squared. It's going to be x and x. There's only one set of factors that work for x squared and 1, so we can go on and throw them in. Now, 4 has 2 sets of factors, 1 and 4 or 2 and 2. Which one of these sets of factors do we want to try first? 2 and 2. And lastly, we can check this here. So we'll do 2x times negative 1 is negative 2x. Negative 1 times 2x is negative 2x. And 2x minus 2x is negative 4x. Face forward. Thank you. So any questions on this so far? Now again, I said this was one of our special cases, or kind of a special type of factors. And if we look at what the 2 factors are, well, the first one is 2x minus 1. The second one is 2x minus 1. So this one here, we could actually rewrite it as 2x minus 1 squared. We could write it in either form. We could write it as 2x minus 1 times 2x minus 1, or we could rewrite it just as 2x minus 1 squared. Either one of these works. And they actually give these quadratics the special name of a perfect square trinomial, because we can rewrite it as a single set of parentheses squared. Now these do have a special formula to them, because it's said that it's a squared plus 2ab plus b squared is a plus b squared. You don't have to write that down, because I really feel that trying to figure out, so what a and b is 2 times ab, and working this back out isn't really any faster than just factoring the thing like we normally do. Because y'all can probably do it the way that we did just as fast, if not a little bit faster, than trying to look at this for square root of a, figuring out what a squared technically is and b squared technically is, and then working it that way. So, better off just doing this here. Questions on this? In the other case, because when it is negative, a squared minus 2ab plus b squared is our a minus b squared, because there's 2 different cases. Let's look at this one here. So the next one we have is 16b squared minus 40b plus 25. Is there a greatest common factor? No, 16 and 40 do, but 25 does not. So 2 sets of parentheses with 3 spaces. Now we find the sign. So we look at the third term. If the third term is positive, the signs are the same and they match the sign of the middle term. If the third term is negative, our signs are opposite. So here the signs are going to be the same, and they're both negative. Now they don't always have to both be negative. They could both be positive. It'll still work the same. Now we need to find the factors of the first and third term. In this one here, unlike the first one, we don't have one that's nice, so we just have a single factor like we did with 1. But we do know that we will have b and b. We put it in the first space in each one because b squared came first. Now we need to look at the factors of 16, which is 1 and 16, 2 and 8, 4 and 4. And the factors of 25, which is 1 and 25, or 5 and 5. So which factors of 16 do we want to try first? 4 and 4. And the factors of 5 we want to try for, or 25, 5 and 5. And if we check this here, 4b times negative 5 is negative 20b. Negative 5 times 4b is negative 20b, which does indeed give us our middle term of negative 40b. Or we can rewrite it as the set of parentheses squared. So we could rewrite it as 4b minus 5 squared. Questions on any of this here so far? They're not bad. They're not any different than what we've done before. It just happens that we can condense it to one set of parentheses squared. That's why it's considered a special case. Nothing really else. Do we feel comfortable with these here? Because if we end up doing this one here, it would be 10x plus 9 times 10x plus 9, or 10x plus 9 squared would be the answer for this one here. Too far. Now the next special type of factors or factoring that we're going to look at is this one here. This one here, I find that most students like this one more than the rest that we do. Because this one here, if y'all remember, is called a difference of perfect squares. And the general form for this here is a squared minus b squared is going to factor to a plus b times a minus b. And it'll work this way every single time. So the big thing for this one here is finding out the values of a and b. What times itself gives us each term. Now between these two here, n squared's kind of easy to work with because what times itself is n squared? Just n. So we get n squared. I kind of put the parentheses there so we can see the difference. Because for 25, what times itself is 25? 5. So we have 5 squared. We could put the parentheses around the 5. Without putting the parentheses around n, it just looks like I rewrote n squared again. But a in our case is n. B in our case is 5. So we can just fill it in as n plus 5 times n minus 5. Yes. That's it. Questions on this here? So if we look at the next one, 16n squared minus 9. Is 16n squared a perfect square? What times itself is 16? And then we'd have n squared. 9 is 3 squared. We don't specifically, you don't have to write this out every time, especially if you know what a and b are going to be. Because when we multiply this out, we'll have a plus b, so 4n plus 3, times a minus b, so 4n minus 3. So the two sets of parentheses look almost the exact same, except for the signs are different. And that's it. Questions on this here? We feel comfortable with these? So I feel like we're ready for the next one, yes? A to the fourth minus 9. Yes. Because a to the fourth is the same as a squared squared. Because a squared times a squared is a to the fourth. It is a perfect square. 9 is 3 squared. So we can rewrite this as a squared plus 3 times a squared minus 3. Even though it's to the fourth power, it still works the exact same. Questions on this so far? So difference of perfect squares. Well, this here is a sum of perfect squares, which we don't have a formula for. It doesn't factor. But the other one, we do have a squared minus 3. A squared is a perfect square, yes? Is 3 a perfect square? No. So this is as far as that goes. Now, if we had a number other than 3, so 4, we could have factored that again. Because if we still have a difference of perfect squares, it can still factor. But since 3 is not a perfect square, this is as far as it goes. Questions on this here? Let's look at this one here. K squared minus 36, or k to the fourth minus 36. We'd have k squared squared minus. So this would become k squared plus 6 times k squared minus 6. Is 6 a perfect square? What times itself is 6? Well, nothing. So that's it. Questions on this here? This one here is the last one of this type that we'll look at. So, as y'all have seen already, x to the fourth is going to be x squared squared minus 81. What times itself is 81? 9. So what we'll have is x squared plus 9 times x squared minus 9, yes? Is 9 a perfect square? So we don't have one for x squared plus 9. We don't have a sum of perfect squares. It just doesn't work. So it stays the same. But x squared minus 9 is a difference of perfect squares, yes? Because what times itself is x squared? X and 9 would be 3. So we have x plus 3 times x minus 3. And that's it. So with the fourth powers, we were able to split it, and then we're able to split it one more time. But only one of the two actually did simplify further. And there's kind of a reasoning for that. If we look at this here, x squared minus 9, because it does give us solutions, x plus 3 and x minus 3. And when we solve, we're trying to see what value of x will make both of these be 0. So for x plus 3, it's negative 3, because negative 3 plus 3 is 0. For the other one, x minus 3, well, that's positive 3. 3 minus 3 is 0, yes? So if we were to solve x squared minus 9 and work it out, we would add 9 to both sides, telling us x squared is equal to 9. Square root both sides, telling us x is equal to plus or minus 3. We're good with that. Y'all don't necessarily have to write this. This is kind of explaining why, if we looked at x squared plus 9 equals 0, why we don't have to or aren't able to factor this. Because for this here, if we subtract 9 from both sides, we have x squared is equal to negative 9, yes? Then we would square root both sides, telling us x is equal to plus or minus, well, the square root of 9 is still 3. But because we have a negative inside, it is 3i. Do we have real solutions for that part? No. So that means this here, the x squared plus 9 isn't factorable, because we only factor with real terms, with real numbers. Because if we were to factor this, it would be x plus 3i times x minus 3i. We almost have to solve it and then work our way backwards to get there. Does that kind of make sense? So when we have the plus, we can't factor it past that. Questions on this here? Now, we are not finishing this note sheet today. We're going to finish it tomorrow. So the last thing we're going to look at today is sum and difference of perfect cubes. Sum and difference of perfect cubes. Now, sum and difference of perfect cubes does have an interesting way that it does factor. The signs have a pattern that they follow. Same, opposite, always end on a positive note. So for sum of two cubes, we have plus to begin with. So it's the same, opposite, always end on a positive note. The difference, so we start out with minus. So same would be minus, opposite would be plus, always end on a positive note. The signs will always work that way. Now a and b. So once we find the cubed root of the first and second term, for the first term we'll have a, and the second part we have a squared, a to the 0. So the first term powers are decreasing in the bigger set of parentheses. The second term is increasing in the bigger set of parentheses. So we have b, here is b to the 0, b to the first, and b squared. It follows this general pattern. Now it'll make more sense when we actually work one through. So we look at this first one here, x to the third plus 125. Now our first main step is to, 1, check to make sure that the two terms are perfect cubes, that we can multiply it by itself 3 times. Now for x to the third, well, the cubed root of x to the third is x. Whenever the power and the index of the radical are the same, they simplify out. Now we do need to take the cubed root of 125 in either calculator. So for the graphing calculator, clear that out, we can hit math and go down to the fourth one, hit enter, and type in 125, and it'll tell us that it's 5. In the 30XS, we can type the number 3, second caret key, 125. Hit enter, and it'll tell us that it is 5. In either case, make sure that that 3 looks like it's a little bit smaller and up, not a bigger 3 in front. So doing this tells us 2 things. 1, that this is the sum of 2 cubes, and 2, it tells us what a and b are. So we can set it up next. We have our small set of parentheses with 3 spaces, and then our bigger one with 5. And again, just like with factoring, we'll do signs next. And with the sum and difference of perfect cubes, it's the same, opposite, always end on a positive note. So same, well, our sign that we have is plus, so the same would mean that we start off with a plus. Then we have the opposite of it. So the opposite of plus is minus, and always end on a positive note. So we have plus, minus, plus. The next thing we're looking at is the first term. Our first term is x. So in the smaller set of parentheses, first term is x. In the bigger set, our first spot is going to have x squared, then x to the first, and then the last one is x to the 0. But anything to the 0 power is 1, well, except for 0. And we have this here. Questions on this here before we look at the second term? Our second term is 5. In our first set of parentheses, we'll just put 5. In the bigger set, x squared would have 5 to the 0, which is 1, so we don't have to include it. The middle one will have 5 to the first, and then the last one will have 5 squared. Questions on how we got to this point here? Now at this point here we can simplify. Our first set of parentheses is going to be x plus 5. Now our next part is simplifying the bigger set of parentheses. Hope you get to feeling better. Yeah. Now simplifying x squared is just, well, x squared. Then we have minus 5 times x plus 5 squared is 25. So we get this here. Any questions on this so far? Not too bad. Because once we get the pattern, and especially after seeing this once before, hopefully these are getting a lot easier to work with. Let's look at the next one. X cubed minus 64. Well, we can start off by taking the cubed root of x to the third and the cubed root of 64. Well, taking the cubed root of x to the third is pretty easy. It's just x. Now, the cubed root of 64 is 4. Our signs are going to be the same. Opposite always end on a positive note. So our starting sign is minus, so for it to be the same is minus. Then we'll have plus and plus. Now on any of these here with the sum or difference of perfect cubes, you will never have one that factors with having 3 pluses or 3 minuses. We will always have 2 pluses and 1 minus. Now when we look at the first term, our first term is x. So in the first parenthesis we'll have x. We're going to have x squared, x to the first, and no x. Now yes, we will have 4, giving us x minus 4. We don't have to put anything with x squared. The middle one will have 4 to the first, and then we'll have 4 squared. Now I have seen a few of these pop up on ACT questions, factor the following polynomial, and they'll pull this up here. Now realistically at this point, you would most likely have the correct answer, because any of them that don't have x minus 4 as one part of the answer, you can get rid of those. And there's probably going to be one that's going to give you 64 as the third number here. That's gone because that's way too big. 64 is not going to show up. But if we simplify this down, we get x minus 4 times x squared plus 4x plus 16. So especially factoring this on the ACT, one, I'd be checking for signs, because that's easy to fix or easy to see. Since it started off as minus, we need minus plus plus. Any of them that don't have minus plus plus are gone. Any of them that are too big, we can remove and start eliminating them. And doing this will hopefully help you to not have to solve all of it or factor it all the way out on the ACT. Now this here is the last one of the sum and difference of perfect cubes that we'll look at for this here. or well, not the last one. We'll look at one more after this. Now we'll start off by taking the cubed root of 27a to the third and the cubed root of 64. Well, one of these two we do know already. The cubed root of 64 is 4. We just had it on the last problem. Now, the cubed root of 27a to the third, we can't type that whole thing into the calculator, mainly because the calculator needs a value for a, which it doesn't have. But we do know that the cubed root of a to the third is just a. Now, the cubed root of 37, we can type it into the calculator. 27 is 3. So this here is 3a. Two and 3. So our signs, since it started out as plus, is going to be the same. So plus, minus, plus. And again, for ACT, that will eliminate at least one, if not two, of the 5. Our first term is 3a. So here we'd have 3a. Here we'd have 3a squared. 3a to the first, and then we won't have a 3a in the last spot. Our second term is 4. So in the first set, we'll have 4 to the first. We won't have anything in the first spot with 3a squared. In the middle, we'll have 4 to the first, and in the last one, we'll have 4 squared. Any questions on how we got this set up here? Now, in simplifying, our first parentheses is going to stay as 3a plus 4. Here, we have 3a squared. We have to square both terms. 3 squared is 9, and we have a squared. So it would be good to pay attention and make sure you square both the 3 and a, not just a. Now, the middle one, minus 3a times 4. Well, 3 times 4 is 12a. Plus 4 squared is 16. And if we were asked to solve, there would be only one solution, one real solution, because any solutions that come out of the quadratic of a sum or difference of perfect cubes is always complex solutions. Questions on this here before we look at the last one? This one is indeed the last problem that we'll look at today. We'll leave factoring by grouping for tomorrow. Well, we can go on and look at the cubed root of 192. So can we take the cubed root of 192? No. But is there a greatest common factor between these two? 9's a little too big. How about a third of it? Because if we add these three up, 192, 1 plus 9 is 10, plus 2 is 12. Is 12 divisible by 3? So 192 is. Now, if I take 192 and divide it by 3, we get 64. And we already know that 64 is a perfect cube, because we've used it at least 3 times today. So if I divide 192 by 3, we get 64 x to the third. Minus 81 divided by 3 is 27 y to the third. We'll go on and do this anyways, even though we know these are both perfect cubes. The cubed root of 64 is 4, and the cubed root of x to the third is x. The cubed root of 27 is 3, and the cubed root of y to the third is y. So we do have our first and second terms. Now we do need to do the signs first. So since our starting sign was minus, the same would mean we'd start off with minus. Opposite would be plus. Always end on a positive note. So minus, plus, plus. Now looking at the first term, our first term is 4x. So in the first set of parentheses, we'd have 4x. In the bigger set, we'd have... So we have 4x squared, and in the middle one we have 4x. Our second term is 3y. So in our first set of parentheses, we'd have the 3y. We don't put anything in with the 4x squared because it would simplify to 1. The middle one will have 3y to the first. And the last one will have 3y squared. Now, just like the factors that we did yesterday and the ones we did before, if it has a greatest common factor, it does need to be included in the answer. Now, 4x squared, we have to square both terms. 4 squared is 16, x squared, plus 4 times 3 is 12, x times y is xy, plus 3 squared is 9, and y squared is y squared. And so that's here, this here would be how it factors. Any questions on this here? And what's interesting with any of this here is that as long as these two terms are perfect squared, or it can be rewritten as a number times itself 3 times, or a term times itself 3 times, it works with any of them. And that's kind of why this is interesting, or why some of this I find unique or really intriguing, is because stuff like this here, it works every single time, no matter how it's set up. As long as they're 2 cubes being added or subtracted, it'll still work. Because we could have x to the 8th minus 1 technically, because 8, let's see here, it wouldn't be 8. I was thinking of 6. Because you don't have to do this one here, because x squared to the 3rd, because powers of powers multiply. So this still works, because we'd have x squared minus 1 times x to the 4th plus x squared plus 1. Still works, follows the same pattern, it just looks a little different. And this would technically factor to x squared minus 1 is a difference of perfect squares. But that's above and beyond. So we're going to stop here for